Hi everyone, today a video looking at haloalkanes for A-level chemistry. So a haloalkane has an alkane skeleton and we've replaced one or more of the hydrogen atoms with a halogen atom. So we've taken our standard alkane, just made of CC and CH bonds, and replaced at least one of these hydrogen atoms with a halogen atom. Now the general formula for an alkane, remember, is CnH2n plus 2. And so the general formula for a single halogen atom haloalkane is CnH2n plus 1x, where x is whatever halogen we've put on. And quite often it's just shortened to be Rx, where R represents the kind of carbon chain. And when we name haloalkanes, we use the prefix fluoro, chloro, bromo, or iodo to tell us which halogen is present. And we do our standard IUPAC rules for naming. So we always have to make sure we look for our longest carbon chain first. The position of the halogen where it is numbered. So we, again, remember to look for that longest carbon chain first, but number where the halogen is. We always want the lowest number possible, remember. If we have multiple of different halogen atoms, then we need to use the prefixes di, tri, tetra to tell how many of each halogen atom is present. And remember that we have to number where everything is, but we have to name everything in alphabetical order, not numerical order. And the suffix is just the alkane ending. So some examples shown at the bottom right. First one is just iodoethane. So this is based off an ethane chain, 2 carbons long. So the ending, the suffix is ethane. We just have one halogen atom, and so we have the iodine. We don't have to number it because if it was on the other carbon, that would still be the first carbon because we always want the lowest numbers. So it's just iodoethane. The second one across, here we have 3 carbons. Our longest chain is 3 carbons long, so it's based off a propane chain. We have a chloro group, and that's on the second carbon in the middle. And so therefore this is 2-chloropropane. And then finally our third one across, our longest carbon chain here, again, is 3 carbons long. We want the lowest numbering possible, so normally that tends to be whichever one the halogen is on is first. And so here we have our carbon number 1 going from right to left, so it's carbon number 1 is on the right, carbon number 3 on the left. So we have our bromo group. We also have a methyl group, a CH3 group coming off the chain. That's at the 2 position. And so this is called 1-bromo, 2-methyl-propane. Remember, in alphabetical order. Now, haloalkanes can also be classified by how many carbon atoms this CX bond is attached to. So, a primary haloalkane, we've got our CX bond, and that carbon that the halogen is attached to is bound to one other carbon-based group. That's a primary haloalkane. If the CX bond, the carbon of that CX bond, the carbon the halogen is attached to, is attached to 2 other carbon groups, that's a secondary haloalkane. And then finally, if we have our halogen being attached to a carbon that is attached to 3 other carbon-based groups, that is a tertiary haloalkane. Now, haloalkanes contain a CX bond. Remember that X just represents a halogen atom. It could be a fluorine, a chlorine, a bromine, an iodine. But for either one of those, that CX bond is always polar. There is a dipole that is created because our halogen atom is always more electronegative than the carbon atom is. So we can draw out our delta positive on the carbon, delta negative on the X on the halogen atom, and we have a dipole that I've shown with this arrow. Dipoles always go from positive to negative, and so our dipole goes towards the halogen atom, which is more electronegative. It pulls the electrons towards itself in that carbon halogen covalent bond. And remember that those partial charges show, the delta positive and delta negative show a partial charge. Now, as you descend to group 7, the electronegativity decreases. Remember that the fluorine is our most electronegative atom, and as we go down from chlorine to bromine to iodine, this electronegativity decreases. Remember, electronegativity is to do with how well we can pull the electron density towards us. As we descend the group, these electrons go into further and further outer shells. They get further and further away. They're less close to the nucleus, and therefore they're less, in terms of electrostatic attraction, less easily pulled in. Now, the polar CX bonds are actually not polar enough to make haloalkanes soluble in water. And so, therefore, the main intermolecular forces that actually really exist are dipole-dipole attractions, permanent dipole forces, as well as van der Waals forces, which of course exist between all molecules and increase with the number of electrons, the size of the molecule, essentially. So haloalkanes tend to mix pretty well with hydrocarbons and other non-polar solvents. Now the boiling point depends on the number of carbon and halogen atoms. So the boiling point increases with more carbon atoms. This is because we have therefore an increased chain length and therefore increased van der Waals forces, more electrons, more atoms essentially, bigger mass. And also if we have heavier halogen atoms, i.e. we are lower in group 7, and this is because again we have more electrons and therefore stronger van der Waals forces. Stronger intermolecular forces means that we have a higher boiling point. It takes more energy to break that intermolecular force. And as with other homologous series, increasing branching of the carbon chain will tend to lower the melting point because these chains can pack together less efficiently. There's less kind of actual space for these van der Waals forces to start interacting with each other. And haloalkanes probably have higher boiling points than the corresponding alkane because they're more polar. So we have some dipole-dipole forces occurring, as well as just van der Waals forces that we have in alkanes, and because they typically have a higher relative molecular mass because they contain a heavier halogen atom than just carbon and hydrogens. So we can then look at the reactivity of haloalkanes. And when haloalkanes react, it's normally the polar CX bond that breaks. And there are two factors that determine how readily that breaking happens, how readily it occurs. The first is the polarity of the bond, the CX bond. Now, if we look to do with the polarity, that's to do with the electronegativity. So we have our electronegativity of carbon, we have our Pauling scale. Carbon is 2.5. And you can see then as we go from iodine up to fluorine, going up groups 17, we have the electronegativity increasing. So iodine is 2.6. Technically, there's a small electronegativity difference there, only 0.1. So not particularly polar, but technically a very, very small difference, all the way up to fluorine where we have a 1.5 difference and a very, very, very polar bond. Now what this means for all cases is that in any case, whether it's fluorine, chlorine, bromine or iodine that we have attached, our carbon is slightly positive, delta positive, and our halogen atom is partially negative, delta negative. What this means is that our electron deficient carbon atom, delta positive, electron deficient, it can be attacked by nucleophiles. And remember, a nucleophile is an electron pair donor. So it's typically a reagent that is electron rich or has electron rich areas. It could have a negative charge, a lone pair, it could have a pi bond, for example. Anytime there's kind of increased electron density around somewhere. Now, due to the highest difference in electronegativity, it would be expected that the CF bond would be the most reactive. It's the most polar bond and therefore the most electron deficient carbon and therefore the most readily attacked by nucleophiles. However, the other factor to consider is the CX bond enthalpy, the strength of the bond. Now we can see from the table on the right here that as we descend group 7 or group 17, the CX bond gets weaker going down that group. We start from a carbon-fluorine bond at 467 kilojoules per mole, all the way down to a carbon iodide bond at 228 kilojoules per mole. Now as we go down the group of the halogens, the shared pair of electrons in the bond gets further away from the halogen nucleus because the halogen gets larger, the electron goes into further outer and outer shells. And so actually the overlap of the electrons with the carbon atom becomes weaker. From a more technical perspective, we can think about it in terms of the electrons in orbitals, this kind of these clouds of charge, these clouds of electron density. As we go down the group, the atoms get bigger. These orbitals and the clouds of electron density actually become bigger as well and more diffuse, and they actually overlap less effectively with the carbon-based orbitals. So the key thing is, as we descend it, the bond becomes weaker. Now, due to being the largest halogen, the carbon-iodine bond has the lowest bond enthalpy, and hence that is the weakest bond, and that would be expected to break the most easily. So we have two opposing arguments here, the CF bond being the most reactive because it's the most polar, or CI bond being the most reactive because it has the lowest bond enthalpy and therefore it's the easiest to break. And actually, through experimentation, it has been shown that the reactivity of the CF bond increases down the group. So a carbon-iodine bond is more reactive than a carbon-bromine, more than a carbon chlorine, and more than a carbon fluorine. So it is the bond enthalpy and not the actual polarity that is the most important factor. So, time to have a go at a few quick questions here to do with naming and properties. So if you want to have a go at the questions, pause the video and the answers will be on the next slide. So the first few questions here were to look at naming molecules. So I've drawn them out on the previous slide in the displayed formula. Here on this slide I've actually drawn them out using skeletal formula. But the naming conventions always stay the same. So our first one, we have to look for our longest carbon chain. Our longest carbon chain is 5 carbons long. Now we always want the lowest numbers, and we'll get those if we number from right to left rather than from left to right. So we have an iodine on the second carbon, a bromine on the third carbon. Remember though that we name it alphabetically and not numerically. So this is 3-bromo, 2-iodo-pentane. Remember, to name the halogens, we use the prefix of bromo, iodo, chloro, fluoro, and the suffix is always just the standard alkane ending. And then for B, again, we need to look for our longest carbon chain. Again, our longest carbon chain here is 5 carbons long. Then we need to consider what we have. We have 3 bromine groups, we have 2 chloro groups, and we have a methyl group that is sticking out, a CH3 group sticking out of the chain as well. Now again, we can number from right to left or from left to right. Again, we get the lowest numbers if we number from right to left. So we have our 3 bromo groups on carbon number 1, our methyl on carbon number 2, and our 2 chloro groups on carbon number 3. Again, remember that we have to use the di-tri-tetra to number how many there are, and we have to make sure that we name it in alphabetical, not numerical order. So this is 1,1,1 tribromo, 3,3 dichloro, 2-methyl-pentane. And then finally, which of A and B has the highest boiling point and why? Well, it would be B. It has a greater relative molecular mass, a greater MR. Therefore, there are stronger van der Waals forces that requires much more energy to break apart and therefore to boil, to break those intermolecular forces. So because we have a longer, essentially a longer chain and more halogen atoms, a bigger MR, bigger molecular mass, stronger van der Waals forces, higher boiling point. Now, we talked earlier about the fact that that carbon X bond can be attacked by nucleophiles. So nucleophiles, we said, were electron pair donors. They tended to have some region of electron density, sort of excess electron density. So it could be a negative charge, it could be a lone pair. And so nucleophiles that will attack and form bonds with electrophiles. Now, an electrophile is the opposite. It's an electron pair acceptor. And essentially what we have here is some kind of electron deficient carbon atom. So it could be a carbon atom that's fully positive, like a carbocation, or a carbon atom that is partially positive with that delta positive symbol, like we have in a haloalkane. So our nucleophile is often a negatively charged ion or an atom with a delta negative charge. It typically has a lone pair of electrons, normally situated on an electronegative atom with which it can form a covalent bond. And so some examples are shown below. You have the hydroxide ion, OH-, cyanide anion, Cn-, the negative charge there on the lone pair on the carbon. That's an exception to this rule of it going on the more electronegative atom. Ammonia, NH3, doesn't have a negative charge, or water, H2O, again, no negative charge, but both contain lone pairs of electrons. Now, these species, these nucleophilic species, will replace the halogen in a haloalkane. So they are called a nucleophilic substitution reaction. We are substituting the haloalkane for whatever our nucleophile is, so it's a nucleophilic substitution reaction. And these follow always the same reaction mechanism. Remember that our mechanism is our series of elementary steps, our series of kind of single chain steps that may involve short-lived intermediates that when we combine them all together gives us the final product. It's like taking lots and lots of photos at a kind of an atomic scale of all the kind of individual snapshot steps that make up the overall change. But the overall arrow pushing of the mechanisms for these mechanisms is exactly the same. Remember that when we're drawing mechanisms, we have to show curly arrows. Curly arrows show the movement of an electron pair, 2 electrons, and they always start from a region of electron density. So that could be a lone pair, could be a negative charge, it could be the middle of a bond, the middle of a single bond or a double bond, some region of electron density, and they end at a region of electron deficiency. So they always move from high electrons to low electrons essentially, and so they end at an electron deficient point. So that could be a positively charged carbon in a carbocation, or it could be a delta positive carbon as we see here. So our mechanism, we take our nucleophile, I'm just representing it here as Nu. We have our negative, could be a negatively charged thing like the hydroxide anion, show the lone pair typically, and we have our arrow starting at the lone pair, ending at the delta positive carbon. So the nucleophile there is our lone pair, or whatever it is. Our electrophile is our haloalkane, our electron deficient carbon atom, delta plus carbon. It's always a good idea to show the partial charges as well. And then carbon can only have 4 bonds, so we have to kick off one of the bonds, and the one that we do is the carbon X bond. And so we have an arrow that starts from the middle of that carbon X bond where the electron density is, and it moves on to the electronegative X atom. The X atom, whether it be a fluoro or a chloro or an iodo, whatever it might be, electronegative, happy to accept electrons, and so our arrow goes from the middle of that bond, ending up on that X atom. And so overall, we've now replaced that X with the nucleophile, and the halogen that we've kicked off gets kicked off with accepted electrons, so it's a halide ion now, X minus, and we call this the leaving group. And remember that when we draw a mechanism, we always have to remember that every step balances in terms of charge and in terms of atom numbers. And so overall, on the left-hand side, we have an overall negative charge from the nucleophile. So we have to make sure that we have an overall negative charge on the right-hand side, and that comes from our leaving group. Now, the rate of reaction depends on the halogen. We said that the key factor in this actually wasn't the polarity, but actually was the bond enthalpy. So carbon-fluorine bonds are the strongest bond that we have, because fluorine is the smallest halogen. The electrons are closer to the halogen nucleus. They're more available there in terms of overlapping of orbitals. And so CF bonds are typically unreactive because of the really high bond enthalpy. But as we descend down the halogen group, the CX bond gets weaker and weaker, and hence the rate of substitution increases. So we can look at a fair few examples of these mechanisms in action. Remember that the mechanisms always follow the same general arrow pushing for this nucleophilic substitution type. So haloalkanes will react slowly with aqueous potassium hydroxide or sodium hydroxide under reflux. The reaction rate can be increased by warming the mixture. We know from sort of really simple kinetics that we can increase the rate of reaction by heating something up, because the collision frequency increases, the particles have more energy, therefore more successful collisions. We typically use a hydrocarbon solvent because, as we said, haloalkanes are not water soluble. They don't dissolve in polar stuff, but they will in non-polar solvents like hydrocarbons. This is called a hydrolysis reaction because we're using aqueous potassium hydroxide or sodium hydroxide. Key thing there being aqueous, we're in water. And the solvent's really, really important, as we'll see later. For this to work, it has to be aqueous, not alcoholic. So aqueous, not alcoholic. Now, the rate of the reaction will depend again on the strength of the CX bond. Fluoroalkanes do not react at all, while iodoalkanes react very quickly because they have the weakest CX bond enthalpy. And so overall, what we've done in this example here, for example, is take our aqueous potassium hydroxide or sodium hydroxide. Essentially, what we consider it to be is a hydroxide anion, OH-. We have our arrow going from the lone pair on the hydroxide anion, starting from there, moving to the electrophile, which is our haloalkane, to the delta positive carbon, the electron deficient carbon. Now, I've not shown the delta positive and negative charges, but it's always a good idea to. And then carbon can only have 4 bonds, so we have to break one of the existing bonds, and the one that we do is the CX bond. So an arrow from the center of that CX bond, where the electron density is, moving on to the electronegative X atom and kicking it off. Again, make sure that our atom numbers and our charges balance on either side. They do. And so overall, what we've done here is converted a haloalkane into an alcohol. Haloalkanes will also react with cyanide ions, that's Cn- ions. And so we can take a haloalkane, react it with our Cn-. We now produce something called a nitrile. That's where we have a Cn triple bond. That's a nitrile. And we kick off our halogen as a halide ion here. So again, a nucleophilic substitution. We do this actually in an alcoholic solvent. And again, the rate of reaction depends on the strength of the CX bond. The product is the nitrile. And the key thing is that it contains one more carbon atom than the starting material. So it's useful in industry because we can increase our carbon chain length by doing this nucleophilic substitution reaction using a cyanide anion. So if you ever see a question where the product has one more carbon in than the reactants did, we've used a cyanide anion to do this. Now nitriles are named using the suffix nitrile, and the carbon of the CN group is counted. So if we look at our example here, for our mechanism we have our cyanide anion, that's our nucleophile, as our lone pair. Arrow from the lone pair showing the movement of those two electrons, ending up at the electrophile, the delta positive carbon in the haloalkane. Carbon can only have 4 bonds, so we break the CX bond, so an arrow from the centre of that carbon X bond onto the electronegative X atom. This then produces a compound called propane nitrile. So it's just simply the carbon chain is three carbons long. We name it using the suffix nitrile. We keep the E in propane, and so it's propane nitrile. Now nitriles are very synthetically useful because not only have we increased the carbon chain length, but there's lots of reactions we can do with these nitriles. We can reduce them down to amines. So remember that reduction is the addition of hydrogen, essentially. So we add hydrogen to it, and we reduce our nitrile all the way down to an amine. So we add hydrogens onto the nitrogen and the carbon. Or we can hydrolyze our nitrile with water, and this ends up producing a carboxylic acid. So we can end up starting off with a haloalkane, getting very easily to the nitrile functionality, and then from there very easily getting to the carboxylic acid or to the amine functionality. Another nucleophile we can use is ammonia, NH3, again alcoholic this time, not aqueous. And haloalkanes will react with excess ammonia. Now the key thing there is excess ammonia. You can see in the equation here, when we write it out, Rx plus ammonia, we form our amine. So we have our substitution, Rx becomes RNH2. So we've had our haloalkane becoming an amine. We've also produced this salt, NH4X, this ammonium salt. So this is why we need 2 moles of ammonia. Again, the rate of reaction depends on the strength of that CX bond. So iodoalkanes react faster than fluoroalkanes. The product is called an amine. They are named with the suffix amine. So we just look for our longest chain again. In this example, our product has 2 carbons based off an ethyl chain. And then we use the suffix amine, so it's ethylamine. Again, the mechanism looks similar, but this time there's an extra step involved. And the key thing to remember is that every step of a reaction mechanism must balance in terms of charge and must balance in terms of atoms as well. So the first step of this mechanism is exactly the same. We have our NH3, our nucleophile, contains a lone pair. We have our curly arrow showing our electron movement to the region of electron deficiency. That's our delta positive carbon. Carbon can only have 4 bonds, so we have to break one of those bonds. We break the CX bond, and so we have an arrow going from the centre of that CX bond, where the electron density is, onto the electronegative X atom. And so this ends up producing the same thing that we've seen for lots of other of these mechanisms. Our NH3 group has substituted on. We've kicked off our X as an X minus. The key thing is, though, that remember all our charges and atoms need to balance. So overall, we started off with a neutral nucleophile and a neutral electrophile. By kicking off our X minus group, we've therefore got a negative charge. We have to have a positive charge, therefore, somewhere else to make it overall neutral. And the positive charge is actually on the nitrogen. This is because when we've used our NH3 to make a covalent bond to the carbon atom, our nitrogen now has 4 bonds attached to it, 3 of them being hydrogen, 1 of them being carbon. And because we have a 4-bonded nitrogen, that's a positive charge on the nitrogen. And so this positively charged amine, if you like, is not the stable final product. This is why we now need 2 moles of ammonia, because another mole of ammonia will come in and will take one of the hydrogen atoms off that NH3 positive group. And so the arrows that we see, essentially our NH3 is acting as a base, taking away a proton. We have an arrow from our lone pair on the second NH3 molecule. Now we can't attack the actual fully positive nitrogen here, the reason being that nitrogen doesn't have any real electron deficiency. It's positively charged, but it doesn't have any, it has 8 valence electrons, it has 4 bonds. So it's got the required number of electrons. It's not electron deficient, and therefore there's no kind of empty orbitals to attack into with our nucleophile. Instead, we have to attack our hydrogen atom, one of the hydrogen atoms that's attached to it. That will be delta positive still, because our nitrogen is electronegative. And so we have a delta negative on the nitrogen, technically, and a delta positive on the hydrogen. So we have an arrow from our region of electron density, the lone pair on the NH3, to the delta positive hydrogen atom. Hydrogen can only have one bond, so we have to then break the other bond that it's attached to. And so we have an arrow going from our NH bond, centre of that bond, onto the electronegative nitrogen. And what this ends up doing is forming our neutral stable amine, ethylamine, and we end up forming this ammonium salt, NH4X. And so the excess ammonia is really, really important. The product amine is also a nucleophile. So not only do we have to have two in the reaction equation here, one acting as a base, one acting as a nucleophile essentially. But another really important thing is that the ethylamine that we've produced is actually a nucleophile in its own right as well. The NH2 group still has a lone pair. And due to the presence of an alkyl groups are slightly electron releasing, what we call the positive inductive effect. Alkyl groups tend to just kind of slowly push their electrons slightly towards electronegative species like the NH2 on here. It's a better nucleophile than the original ammonia was. So if we didn't have excess ammonia, it would react with any remaining haloalkane more quickly than the ammonia would. So if we didn't have excess, we'd have our NH3 reacting with this haloalkane, we'd form some ethylamine, and then our ethylamine could act as a nucleophile as well. It reacts more quickly than the ammonia does because it's a better nucleophile. The alkyl groups are electron releasing. They essentially put slightly more electron density onto that NH2, making it a better nucleophile. And so you end up then with this reaction kind of going on and on and on and producing lots of different amines, not just the one amine that you want. Whereas if we use excess ammonia, well, hopefully all of the haloalkane will have reacted with the ammonia by the time that we've made some ethylamine. So there'll be no more haloalkane left to react with the ethylamine. Now, something slightly more advanced, and it's something to just double check with your exam board as to whether they require you to know this or not, is there's actually two different types of nucleophilic substitution, SN1 or SN2. Now, the type of substitution mechanisms we've been looking at are known as SN2. It's a bimolecular process. By that we mean the rate law for this process has two species involved in it. There's an alternative method where we have the initial breaking of the CX bond to form a carbocation. Now this is a unimolecular process, an SN1 mechanism. So the unimolecular just means the rate law only depends on one species. And so here's the sort of key difference. The one that we've been looking at is at the bottom. That's our SN2 mechanism. Essentially we have our nucleophile attacking our delta positive carbon and our CX bond breaking at the same time. So the nucleophile attacks, the CX bond breaks both at the same time. And that step actually is our rate determining step, the slowest step. And therefore that's why the rate depends on both the nucleophile and on our haloalkane. And that then produces in this case, an alcohol and has our leaving group kicked off. And the key thing here is that actually our nucleophile always attacks from behind, 180 degrees behind the CX bond. And so we call this a backside attack. It attacks from the back of the molecule. And what this actually leads to is an inversion of stereochemistry. So it's important if you have enantiomers of these, if you have, maybe potentially you only have one of the enantiomers. If you do this SN2 reactivity, you would end up with the alternative enantiomer at the end, because the stereochemistry inverts. If you haven't got a stereochemically active molecule, you haven't got a chiral molecule, then it doesn't matter essentially. However, the other alternative is an SN1 process. So this is where our CX bond breaks first. So we start from our tetrahedral haloalkane. We have our rate determining step, which is the breaking of the CX bond. That produces a carbocation, positively charged carbon. That's a planar molecule. And we have our X minus, so this is our trigonal planar carbocation. That breaking is the rate determining step, and so that's why our rate law only depends just on the haloalkane, doesn't depend on the nucleophile this time. because the nucleophile occurs after the rate determining step. If you're not happy with this kinetic stuff, you can go and check out my videos on the kinetic series. And then our second step is quite a very quick step, just simple charge attraction between our nucleophile and our positively charged carbon. And so that then produces, in this case again, an alcohol. And the key thing being that if we had stereochemistry to observe in our product, because our carbocation is a planar molecule, this nucleophile doesn't have to attack from a specific kind of 180 degrees behind it. It can attack from either above or below with equal probability. And so we end up, if we do end up creating a chiral molecule with stereoisomers, we would create what's called a racemic mixture, a 50-50 mixture of the enantiomers. So SM1 actually is favoured for tertiary haloalkanes. Remember, a tertiary haloalkane was where we have 3 other carbon groups attached to the carbons attached to the X group. The reason for this is because we can end up forming a stable tertiary carbocation. So out of all the different carbocations, a tertiary carbocation is the most stable. Whereas typically an SN2 mechanism is preferred for a primary carbocation, because the key thing that stops that occurring is having what we call a sterically hindered molecule, a very kind of crowded molecule where we can't get sort of 180 degrees behind it. We have to attack from that very specific angle. So we can also do a nucleophilic substitution reaction but using water. Now haloalkanes react very slowly with water because water is a pretty poor nucleophile. It's not a very good one. So the rate of reaction is pretty slow. But it will react over time, and we end up having our RX, our haloalkane, plus water to produce our alcohol, ROH, plus HX. So it looks very similar to if we just use a standard hydroxide anion. So we saw that reaction of aqueous potassium hydroxide or sodium hydroxide. Here we're using water, so the only difference is we have an extra hydrogen, and so we end up forming HX rather than just X minus. But the reaction is useful, even though it's slow, because it can distinguish between chloro, bromo, and iodoalkanes. Because if we add some silver ions in, they will form precipitates with the silver ions, and these precipitates have different colours and also different solubilities. Now, just a key thing to point out, we can't actually distinguish if we have a fluoroalkane because the silver fluoride is soluble. It's not a precipitate in water, and so it can't be identified. So the first thing I'm going to do is add my water to the haloalkane. Sometimes you'll see ethanol being added as well. That's just to make the haloalkane and the water a bit more miscible, or they make them mix together better. Remember, haloalkane is not soluble in polar stuff like water. Then we're going to add dilute nitric acid, HNO3. And the reason that we're going to do this is because there might be some impurities that would give us false positives by also forming precipitates. And the two that we have to really worry about are silver carbonate, Ag2CO3, and silver hydroxide, AgOH. If we have some carbonate or hydroxide anions as impurities in our test tube, these can also form precipitates when silver is added, and therefore that would give us false positives in our test where we're looking for precipitates. And so the way that we get rid of them is by adding acid. It's the standard reactions really that you're used to seeing. Acid plus carbonate gives carbon dioxide plus water. Hydroxide, which is a base, plus the acid gives us water. And you can see here that I've written the kind of sort of ionic equations out for this. We have our carbonate anion reacting with the acid to produce carbon dioxide, water, and then our NO3 minus anions, which are the spectator anions. And likewise, we can have OH minus plus H plus and NO3 going to H2O, water, plus the NO3 again, the NO3 minus being spectator ions. Now, we can't use sulfuric acid, H2SO4, because silver sulfate, Ag2SO4, is also a precipitate. So again, it's another one of these examples where it would produce a false positive. So we can't use that. Also, just to say that precipitate is often just abbreviated to PPT. And we can't use HCl because if we're looking to do a test to see if we have any chloroalkanes, the last thing we want to do is to put an acid in that contains chlorine, because that's going to give us, again, potentially false positives and would eventually end up forming a silver chloride precipitate, even though we might not have any chlorine in our haloalkane. So then once we've done that, we're going to add a few drops of our silver nitrate, AgNO3, and the silver halide precipitates form. And so the key reaction is the silver nitrate, AgNO3, reacts with the HX that we formed from doing our nucleophilic substitution with water This produces our silver halide, AgX, that's our precipitate, that's solid, and then we have reforming nitric acid. The first key thing is that these silver halide precipitates are actually different colours. So silver chloride is a white precipitate, silver bromide a cream precipitate, and silver iodide a yellow precipitate. Now, I've shown the colours over there on the right, but as you can see, those colours aren't the best way to necessarily distinguish it. You might be able to tell whether you had a chloro versus an iodo, but generally they're fairly hard to distinguish. Colour is quite subjective. And so a better way to then carry on this test is to use the fact that these precipitates actually have differing solubilities in ammonia solution. So the first thing I'm going to do is add some dilute ammonia solution. This will dissolve up the silver chloride precipitate, but will leave the silver bromide and the silver iodide as precipitates. It can't dissolve them up. And so the key reaction really is our AgCl, our silver chloride, reacting with ammonia solution to produce this complex silver ion, this silver diamine ion. Now you might recognise that ion there as actually being Tollens reagent if you've covered some of the alcohols videos potentially, or the aldehydes and ketones videos on this channel, but that's the key reaction that goes on. If a precipitate remains, we can then add concentrated ammonia solution. Now concentrated ammonia solution will dissolve the silver bromide precipitate, but it won't dissolve the silver iodide precipitate. It can't dissolve that silver iodide up. And so the key reaction here is AgBr plus NH3 going to be this diamine silver complex again, this complex ion. And therefore we know that if a precipitate remains, it must be the silver iodide. And so we can kind of logically work it out by first doing dilute ammonia. If it dissolves, it's silver chloride. If it doesn't, it must be bromo or iodine. We then add concentrated ammonia. If it dissolves, the silver bromide was present. If it doesn't, it was the silver iodide that must be left. Now you can also do this test using hydroxide anions. Essentially the same steps follow. It's just that you're using hydroxide anions rather than water. So you end up forming X- rather than HX. And the reaction tends to go a bit quicker as well. But the key thing here of adding the silver nitrate to form the AgX, that precipitate, is the same, as well as using the ammonia solutions to look at the solubilities. Now, nucleophilic substitution is a very useful type of mechanism to do, and haloalkanes are very synthetically useful because substitution reactions are a way of introducing new functional groups into organic compounds. And these new functional groups can often then be further reacted. And so in just a few steps, we can end up really with a completely different functionality in the molecule. So for example, we can take our haloalkane, and right away, by looking at the reactions we've seen on the previous slides, we can use aqueous hydroxide anions to get to an alcohol. And then we know from alcohols, we can oxidize alcohols up. We can go from alcohols, if we have a primary alcohol, to an aldehyde and up to a carboxylic acid. If we have a secondary alcohol, which is not shown here, we'd be able to get up to a ketone from that by oxidizing it with potassium dichromate that's been acidified. If we use our cyanide anion, we saw that we generated a nitrile. We've increased the carbon chain for one, so that's synthetically useful. But we said that we could reduce this nitrile down to an amine, or we could hydrolyze it to a carboxylic acid. And then also we saw we can use ammonia, NH3. This can produce a primary amine. And we said from that if we didn't really control how much ammonia we used, if we didn't have excess ammonia, that our primary amine was a better nucleophile than the ammonia was. And so the reaction goes on and on. That produces a secondary amine, which can produce a tertiary amine, which can go all the way to end up producing something called a quaternary ammonium salt. Now the final type of reactivity we've not talked about, but which we're going to talk about in a minute, is this going from a haloalkane to an alkene. This is something that we call an elimination reaction. And this is why it was really important to stress that when we used hydroxide, that it was aqueous. Because if we use hydroxide in an ethanolic solvent, an alcoholic solvent, that actually promotes an elimination reaction rather than a nucleophilic substitution. So that's the reason that if we use our cyanide anion or we use our NH3, we can do this in an alcoholic solvent. However, if we use hydroxide, depending on what reactivity we want, if we want substitution, we have to use aqueous hydroxide. If we want elimination, ethanolic hydroxide. So we've just said the solvent can have a huge effect on the mechanism seen. And if the hydroxide ions are in alcoholic solution, such as ethanol, then a different mechanism takes place, and this is an elimination mechanism. So the hydroxide ion here doesn't actually act as a nucleophile and substitute, it actually acts as a base, and this time it removes a proton from a carbon that is adjacent to the CX bond. And this ends up forming an alkene and the loss of the halide ion. The really key thing is that there is no water present at all. Doing it in alcoholic solution means we don't have any water present, and the mixture is heated to try and force the elimination to happen, as well as rather than the substitution, we often heat things as well. And so our mechanism for this is slightly different. So again, we're always going to start from our nucleophilic bit and work to an electrophilic part. So our nucleophilic part is our alcoholic hydroxide anions, the lone pair. This attacks a hydrogen on a carbon adjacent to the CX bond. We then, again, carbon can only have one bond, so we have to break the other bond. So we break that carbon-hydrogen bond by actually having an arrow that goes from the centre of that carbon-hydrogen bond to the centre of the carbon-carbon bond. So that's actually showing you the formation of a carbon-carbon double bond. You can think about the electron density from that CH bond moving in to the carbon-carbon single bond to create a carbon-carbon double bond now. Again though, carbon can only have 4 bonds, so the one on the left has 4 bonds, the one on the right now has 5 bonds, so we have to break something, and the one that we break is the CX bond. And so we have that very familiar arrow of an arrow starting in the middle of the CX bond where the electron density is, ending up on the electronegative X atom. And so overall, we end up forming an alkene, carbon-carbon double bond. Water has been eliminated, and our X minus has also been eliminated as well. Now we can also test for the presence of an alkene by shaking the mixture with bromine water. If you're not sure about this, go and look at my alkene set of videos, but by shaking it with bromine water, we essentially force an electrophilic addition reaction to occur. The bromine adds across, and so we get this decolorization of the bromine water from orange to colourless. Now, a key thing to note why this works is that when we think about our nucleophilic substitution, we have our CX bond where because our X is more electronegative, our carbon is delta positive, our X is delta negative. If our OH minus is acting as a base, well, if we just have a carbon-hydrogen bond, actually hydrogen is more electropositive than carbon. So our carbon now ends up being delta negative, more electronegative, and the hydrogen ends up being delta positive. So this is why it can act as a base, because essentially the H essentially is a proton, if you like, a positive hydrogen, a delta positive hydrogen. Key thing is though, if it's alcoholic OH, elimination, and if we heat it, if it's cold aqueous hydroxide, then it's a substitution reaction. So because the hydroxide anion can act as both a nucleophile or a base, there'll always be competition between substitution and elimination occurring. And normally a mixture of the alcohol and the alkene products actually form. It's really hard to exclusively get one or the other. And so we can see here for an example of 1-chlorobutane that if we use cold hydroxide anions that are aqueous, we can try and force the substitution to happen to make butan-1-ol, nucleophilic substitution. If we use hot hydroxide anions that are alcoholic, for example in ethanol, we can try and force the elimination to occur, to make but-1-ene in this case. Now, there are ways to make the one pathway dominate, so we said the conditions. Hot alcoholic hydroxide will always favour elimination, while cold aqueous hydroxide will always favour substitution. But also the type of haloalkane is really important. So like we talked about how the primary, secondary or tertiary part of the haloalkane was important for dictating whether it was SN1 or SN2, it's also important for dictating if it's elimination or substitution. So primary haloalkanes tend to react through substitution reactions, tertiary haloalkanes tend to react through elimination reactions, and secondary tend to do a mixture of both, essentially. And so we can see here that if we have a methyl haloalkane, or a primary haloalkane, just one other carbon group attached, that typically we get much more substitution and really no elimination. The reason being that the molecule isn't essentially for the substitution to really work. What we want is, certainly for a primary haloalkane, we're going to be going to that SN2 pathway. We need our molecule to essentially have a kind of the backside of it being open to attack, not very cluttered with lots of atoms around it. So hydrogen atoms are very small. It's very easy for it to attack from 180 degrees behind, and so substitution dominates. For a tertiary haloalkane, well, now there's lots of big carbon groups around. It's much more difficult for it to attack. However, we have to, for elimination, remember, we take a hydrogen atom from the adjacent carbon. And so that's much more readily taken. And so therefore, for tertiary haloalkanes, elimination is much more favoured rather than substitution. The last thing really to say with this is that it's possible to get isomeric products. So for some haloalkanes, really, if we have an unsymmetrical haloalkane, where our CX isn't directly in the middle or at the end, we can end up with isomeric alkenes forming from the elimination reaction. And so this example of 2-chlorobutane here, remember that we take hydrogen atoms from adjacent carbons. Here, though, the adjacent carbon could be on the left or the right. If I take it from the left, the blue arrows, I can form but2ene. If I take it from the right, I can form but1ene. So those are our position isomers of that double bond. It's either on the first carbon or the second carbon. So we have some actual structural isomers there. But we can also form geometrical isomers, EZ isomers, that form of stereoisomerism. That's because but2ene can form either the E or the Z geometrical isomer. If you're not happy with looking at E and Z, remember to go back to my videos on alkenes. But essentially, we look to see if we have two heavy groups and whether they're attached to either the same side of the alkene or opposite sides. So for the E-but2ene, our two heavy groups are the two methyl groups. Here we have them in E-but2ene being one above, one below on opposite sides, and therefore it's E. For Z-but2ene, they either have to be both above or below that double bond. Here they're both below it, and so it's Z-but2ene. And remember that it's not possible if we have two of the same group attached to the same carbon. So for but1ene, we can't have EZ isomerization because we have two hydrogens attached to that rightmost carbon. So time to have a go at some questions. So again, have a go at these, pause the video, and the answers will be on the next slide. So the first question then said that we had hot concentrated ethanolic potassium hydroxide reacting with this haloalkane to form two alkenes that are structural isomers of each other. The major product is 2-methyl-but2ene. Name and outline the mechanism for that. So this is an elimination reaction. We have to have our hot hydroxide anion attacking a hydrogen that is adjacent to the carbon-bromine bond in this case. And so the actual arrows that we're drawing here is the green ones. So we attack that left hydrogen atom. We have our arrow from our nucleophile, from the lone pair here, acting as a base, remember, not a nucleophile here. So from the lone pair, taking our delta positive hydrogen from that CH bond. Then we have only hydrogen allowing one bond, so we have to break the CH bond. We have an arrow from the center of that CH bond down into the middle of that CC bond to form the CC double bond. Remember that it forms an alkene, so we have to form a CC double bond somewhere. And then the carbon can only have 4 bonds. The leftmost one has 4 bonds, but the right one, the one in the center, actually has 5 bonds now. And so we have to break a bond, and we break that CBr bond. So an arrow going from the center of that CBr bond to the bromine atom, which is happy to accept those electrons because it's electronegative. And so the key product that we end up making here is the 2-methyl-but2ene. We've lost water and we've lost the bromide anion as well. Note that there's no EZ isomerization possible here as well because we have 2 methyl groups on that leftmost carbon, and therefore if we have 2 of the same group on the same carbon, no EZ isomerization is possible. We're then asked to draw the displayed formula for the other isomer that is formed. We're told here that it's not a geometric isomer, but a structural isomer. And actually it ends up being essentially some sort of position isomer here, where we now have 3-methyl-but1ene. So this can be taking the hydrogen atom from the other adjacent carbon. So this is the blue arrows rather than the green that I've shown. It's exactly the same arrow pushing, just from the other side of the molecule, from the right rather than the left. And this ends up producing 3-methyl-but1ene. And remember that displayed formula means that we have to show every single bond. So make sure we also draw out all the CH bonds as well. Then the type of structural isomerism that's shown is position isomerism, because the double bond is in different positions. And then question B here was to say that another organic compound X can be detected in the reaction. we were given the molecular formula and told it's a secondary alcohol. Draw the displayed formula. So if it's an alcohol, we know that it must have now done nucleophilic substitution rather than elimination. This is an SN2 pathway that we've been talking about before. So normally we'd have to have cold aqueous sodium hydroxide, but we said it's basically impossible to get just one of these to dominate, so we would form a tiny bit of this if we used hot alcoholic hydroxide. And so we draw our arrows as we did before. Our arrow from the lone pair on the nucleophilic hydroxide anion to the delta positive carbon atom. Here you can see I've kind of drawn it from 180 degrees behind as well. Then our carbon can only have 4 bonds, so we have to break the carbon-bromine bond, an arrow from the centre of the carbon-bromine bond ending up on the bromine atom to make a bromide ion. So just drawing the displayed formula, we have our secondary alcohol, 3-methyl-butanol, and again, displayed formula means drawing every single bond. So just one change to the reaction conditions that would increase the yield of X. Well, we could either now use aqueous hydroxide rather than ethanolic hydroxide, or we could use cold rather than hot hydroxide. Either one of those chains would hopefully change it to go more for substitution than elimination. And the type of mechanism we've said is a nucleophilic substitution mechanism. Now the final thing to talk about is actually the formation of haloalkanes. So we've talked a lot about the reactivity of haloalkanes and how we can convert haloalkanes into lots of other functional groups using nucleophilic substitution or elimination reactions, but we haven't talked about how to make a haloalkane to start with. Now one of the ways that we can do this is to actually start from an alkane and halogen. And when you put a mixture of an alkane and a halogen into bright sunlight, or you shine a UV lamp onto the mixture, they actually react together to form a haloalkane. It's the UV component of the light, either from sunlight or the actual UV lamp, that initiates the reaction. Now, alkanes do not react with halogens in the dark at room temperature. They can react at very, very high temperatures, but at room temperature in the dark, they don't react. So if I have my alkane and, let's say, chlorine, Cl2, they won't react together in the dark, but as soon as I put them in bright sunlight or a shiny UV lamp, they will react together. So it's the UV component that starts this. And a substitution reaction takes place. One or sometimes more of the hydrogen atoms in that alkane will be replaced by a halogen atom. And so the reaction is called a free radical substitution. The reason for this is because it involves radicals, unpaired species that have unpaired electrons. So rather than being a nucleophilic substitution, it's a free radical substitution. And it's something called a chain reaction. Essentially what that means is the reaction can kind of be, you can imagine it going round in a circle, and so what you start with, you kind of end up reforming at the end, and it can just kind of go round and round and round. And any reaction between an alkane and a halogen goes by the same mechanism. Now the first step of this is called the initiation step. This is where we have our halogen, it could be Cl2 or Br2, whatever it might be, that gets broken up into 2 chlorine free radicals. Now we denote a free radical, an unpaired electron, with a dot next to the atom. Now, how this works, this has to be, as I said, in the presence of some sort of UV light. And so the Cl2 molecules absorb a quantum of UV light, and the bond breaks what we call homolytically. So it's the UV part that breaks it. It's the fact that it has enough energy to break this bond, the UV component of the light. And when we say it breaks homolytically, what we mean is that it breaks essentially totally in half and evenly. 1 electron goes to each. And this results in the formation of 2 separate chlorine atoms. And these are technically free radicals. They contain an unpaired electron. If we think about just a normal chlorine atom, 7 electrons pair up. So we always have 1 unpaired electron. The next 2 steps are called propagation steps. And so here we have one of our chlorine free radicals reacting with our alkane. So in this case, I'm going to show it as methane, CH4. Now what always happens here is our Cl radical abstracts a hydrogen. We said that it replaces a hydrogen atom, and so our Cl abstracts a hydrogen atom. So we always end up forming HCl, and now we have this, what we call a methyl radical, CH3 dot. So this again has an unpaired electron on it. The next propagation step is to take that CH3, what we've just formed, that CH3 radical, react it with more of the chlorine, Cl2. This produces the actual haloalkane, CH3Cl, and it also regenerates a chlorine radical. This is why it's called a chain reaction. We've ended up regenerating, after all these steps, a chlorine radical, which can then go on to react with even more methane. It can kind of go round and round and round. So the two propagation steps are our chlorine radical reacting with the haloalkane. This always gives us HCl and, in this case, a methyl radical. The second propagation, we take the radical we've formed, we react it with more of our halogen, Cl2 in this case, to reproduce the chlorine radical and to make our haloalkane. And so the effect of these two steps is to produce HCl and CH3Cl, and also a new chlorine radical. And this new free radical can react with more methane and repeat these two steps. That's the chain part. It can happen loads and loads of times. And note how the way I always remember these reactions is it's always radical plus a stable molecule gives you radical plus a stable molecule. And then finally we have what's called the termination steps. Termination steps are where we have any two radicals coming together to produce stable compounds. Essentially it removes the free radicals from the reaction. So this could be two Cl radicals coming together to make Cl2, two CH3 radicals coming together to make ethane, C2H6, or a CH3 radical and a Ca radical coming to make CH3Cl. So it's fairly interesting. If you did this reaction in your reaction mixture, you wouldn't just expect to see the HCl and the CH3Cl. You'd also form some chlorine, you'd also form some ethane, as well as forming a little bit more of your actual haloalkane from one of these termination reactions. And overall, the way we work out the overall reaction is to add our two propagation reactions together. Anything that's on both sides will cancel out. So we have our Cl radical on both sides, our CH3 radical on both sides. They get cancelled out. And so the overall reaction is to take methane plus chlorine, Cl2, to produce chloromethane, CH3Cl, and HCl. And it's always this exact sort of type of mechanism and the products that we form, or the types of products that we form, for example, radical plus stable molecule to radical plus stable molecule is always the same. Now the problem with it is that free radical substitutions are highly unselective. Often large mixtures of products are obtained. Alongside, for the example we have here, alongside the chloromethane and the HCl, we have ethane being formed, C2H6. We could have dichloromethane, CH2Cl2, or trichloromethane, CHCl3, as well as even tetrachloromethane, CCl4. So it's a really, really unselective reaction. It doesn't just stop at taking one hydrogen and go, that's it. It can often take more and more hydrogens. And you can see that if you start off with even bigger alkanes, there's lots and lots and lots more products that could be obtained. So it's not a particularly great way to do it because the reactivity is not easily controlled. With longer chain alkanes, tons of isomers end up being formed because any of the hydrogen atoms can be replaced. Now, an importance of this for not only making haloalkanes is another type of haloalkane called chlorofluorocarbons. So these are haloalkanes that contain only chlorine, fluorine, and carbon atoms. They don't contain any hydrogens. So chlorofluorocarbons, clues in the name. So this could be CCl3F or CCl2F, for example. Now these are very, very unreactive under normal conditions. We said that the carbon-fluorine bond was extremely strong. The carbon-chlorine bond is also fairly strong. So just under normal conditions, these are pretty unreactive molecules. And the short chain ones are gases and were used often as aerosols and refrigerants, for example. The longer chain ones were used as dry cleaning solvents. However, these CFCs eventually end up in the atmosphere. And in the atmosphere, where we have this UV light component being much stronger, they decompose to give chlorine radicals. Now, chlorine radicals actually go on to decompose ozone. And note that ozone is O3. And this happens in the stratosphere, and it causes a hole in the Earth's ozone layer. So this is what is causing partially the depletion of the ozone layer. Now, CFCs are being phased out and replaced with hydrochlorofluorocarbons, HCFCs, and hydrofluorocarbons, HFCs. These are much, much safer. But the actual reactivity is exactly the same as we've just seen on the previous slide. Initiation, 2 propagation, 1 termination. So our initiation, let's say we start with CCl3F. Our initiation under UV light, remember it's the UV light component of it that causes this bond homolysis. Breaks a carbon-chlorine bond. We form 2 radicals. The important one is the chlorine radical. This goes on in our first propagation step to react with ozone. This abstracts essentially one of the oxygens from ozone to make ClO as a radical and oxygen. Remember, it's always radical plus stable molecule gives you radical plus stable molecule. Then the second propagation step is that radical we've just formed, the ClO radical, reacting with more ozone, O3, to produce 2O2 and chlorine. Again, radical plus stable molecule gives you radical plus stable molecule. And the key things to kind of help you remember this is that the radical we form in the first propagation step is the one that we use in the second propagation step. And again, it's a chain reaction, and so the radical we form at the end of the second step must be the same as the radical we started the first propagation step with. And then our termination, again, it can be any two radicals combining. I'm only showing one here as an example. Two of these ClO radicals combining, and these combine to end up producing chlorine and oxygen. So two radicals combining to give stable molecules. And again, we can calculate our overall equation by combining the propagation steps together, cancelling out the things that appear on both sides. And the overall equation is very simply that we have ozone going down to oxygen. And again, it's a chain reaction, and the really key bit is that one chlorine radical can decompose thousands of ozone molecules before it gets destroyed. So, time to have a go at the question, just on this free radical substitution bit. So to name on the outline, the mechanism for that is shown on the screen there. So if you want to have a go, pause the video and the answers will be on the next slides. So it's a free radical substitution. We can write out the steps. Now you have to check with your exam board whether you need to know the actual curly arrow mechanism for this, which I'll show on the next slide, or whether you just need to be able to write these equations down. But the actual equations are essentially the same as we saw on the previous slide. So we take our initiation step, which is our chlorine under UV light, doing our homolytic fission, breaking it evenly, one electron to each, to produce two chlorine radicals. Our first propagation is a chlorine radical reacting with our chloromethane. It extracts, remember I said it abstracts a hydrogen atom to make HCl. So we form HCl and we abstract a hydrogen atom to now make CH2Cl as a radical. Remember that the propagation steps are always radical plus stable molecule, gives you radical plus stable molecule. Second propagation step, we have to use the radical we've just formed, so CH2Cl, react it with more chlorine. It abstracts one of those chlorines to make CH2Cl2. That's now dichloromethane rather than just chloromethane that we started with. And we reform our chlorine radical. So remember that whatever radical we end up making in the second step has to be the same as the one we started in the first step with. And then I've shown the three termination steps. It's any of the radicals combining, so two Cl radicals forming chlorine, two of these CH2Cl radicals to form C2H4Cl2, or CH2Cl radical combining with a Cl radical to make more dichloromethane. And so overall, we combine our propagation steps together, write everything that's a reactant on the reactant side, everything that's a product on the product side, and cancel out things on both sides. And you're left with CH3Cl plus Cl2 going to CH2Cl2 plus HCl. Now, sometimes exam boards want you to know the actual curly arrow mechanism for it. The actual reactions that we write, the equations we write are exactly the same. It's now just we show them using curly arrows. The key thing is that the arrows we've been seeing for the elimination reaction, the nucleophilic substitution, these are, it's an arrow with a sort of full arrowhead, a proper arrowhead at the end. And it denotes two electrons being moved. When we're considering radical, typically we're considering radical reactions, we're considering one electron moving. Radicals have an unpaired electron, so really it's one electron that's moving. So we use what's called a fishhook arrow, or essentially it's an arrow with one of those sides, a half arrow. So if we draw out our steps for this, we have our initiation, that chlorine-chlorine bond breaking. So we draw a half arrow. We always start from electron density. We don't change any of that, think about in the mechanism of that. Start from our electron density, end up on an electronegative atom. And so we have a half arrow going to each chlorine. That produces our chlorine radicals. And then generally, whenever we have a covalent bond, remember a covalent bond has two electrons in it. And so we have to have one arrow going one way, one arrow going the other way. And so our first propagation is our Cl radical extracting that hydrogen atom. So we have one of those half arrows from the CH bond combining with the Cl half arrow. And then we have to also consider where the other electron goes in that CH bond when it goes onto the CH2Cl. The second step of it is very similar. So we take our CH2Cl, We have our chlorine-chlorine bond breaking homolytically again, so one electron joins up with the CH2Cl, the other goes onto the Cl. And then for termination, we can just draw, for example, two of these CH2Cl radicals combining. We just draw half arrows from each radical joining together. So the key thing is, though, that a radical is a half arrow, or a fishhook arrow. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found this video helpful, please consider leaving a review on the tuition website or social media. I offer online tuition for chemistry. Please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.